A cylinder head is connected to the cylinder flange by means of 12 number of bolts. The inside diameter of the cylinder is 480 mm and the maximum pressure inside it is restricted to 1.5 Newton per mm square. So diameter of the cylinder is known, pressure is known, so we can calculate here the external force exerted on the cylinder flange, which is resisted by 12 number of bolt. If the bolt have a permissible tensile strength of 80 Newton per mm square, determine the size of the bolt neglecting the initial tightening. If for the same application M30 bolts are used, find the number of bolts required. So you have to solve here two cases. In the first case, you have to find out the size of the bolt, and second case, if M30, that is a nominal diameter equal to 30, then how much number of bolts are required, that you have to find out. So this figure represents a cylinder and the diameter of the cylinder is given as 480 mm. So we have value of D is equal to 480 mm. And likewise we have 12 number of bolts are used. So we have N is equal to 12 number of bolt. The maximum pressure inside the cylinder is restricted to 1.5. So we have a uniform pressure distribution here and the pressure P is given as 1.5 megapascal. Product of pressure multiplied by the area of the cylinder will be the external force acting on 12 number of bolt. So we can calculate here the total force Ft, which is the product of pressure multiplied by area. So we have Ft is the total force which is resisted by 12 number of bolt is equal to pressure P multiplied by pi by 4 into d square, that is the diameter of cylinder square. Permissible tensile strength is given as sigma allowable is equal to 80 megapascal. You have to find out the size of the bolt, that is the diameter D0 you have to find out. Let's calculate here total force Ft is equal to pressure multiplied by pi by 4 d square. We have pressure is equal to 1.5 Newton per mm square multiplied by pi by 4 multiplied by d square, which is equal to 480 square. Mm square cancel, we will get this answer in Newton. After dividing by 1000 you will get this answer equal to 271.4 kilonewton. This force is distributed in the 12 bolt, so each bolt has a force equal to Ft divided by 12. So the force on each bolt is equal to F is equal to Ft divided by number of bolt, that is we have 271.4 divided by number of bolt equal to 12. This answer will come in kilonewton. So each bolt carries a force equivalent to 22.62 kilonewton. This bolt will experience a force is equal to F, and therefore the bolt will fail under the tension because it is perpendicular to the cross section area. So we have a failure by tension. In that case, the value of F is equal to the minimum area will be equal at the root. So we have pi by 4 into dc square multiplied by sigma allowable. Force is equal to 22.62. It's a kilo, so we have to take 10 to the power 3, that is Newton, equal to pi by 4 into dc square, and we have sigma allowable is given as 80. If you solve it, you will get the core diameter. In this case, the diameter at the root or inner diameter will be equal to dc is equal to 18.9 mm. And we have given the relation between dc and the outer diameter. So we have outer diameter or the nominal diameter equal to the root diameter divided by 0.84. That is we have 18.9 divided by 0.84. So the nominal diameter DO will come approximately equal to 24 mm. Hence we have to select the bolt M24. M24 means that we have to select the nominal diameter equal to 24 mm. In the second part, if we are using M30 bolts, then you have to find out the number of bolt required. So in the case of M30 bolt, we have the nominal diameter is DO is same as equal to 30 mm. Hence we have core diameter will be equal to 0.84 times the nominal diameter equal to 30. is 25.2 mm. So we'll use the same equation. We have F is equal to pi by 4 multiplied by dc square multiplied by sigma allowable. So this one is a force carried by one bolt, and to find out the number of bolt, we'll use the equation F is equal to Ft by N. So let's calculate here how much force is carried by one bolt, that equal to pi by 4. For M30, the core diameter equal to 25.2 square of it. Sigma allowable will remain same, that equal to 80. This answer will come in Newton. Dividing by 1000, you will get this answer close to 39.9 kilonewton. And finally, to find out the number of bolt, we have number of bolt is equal to the total force exerted due to pressure divided by the force carried by each bolt. Ft value already we have done is 271.4 divided by F is equal to 39.9. You have to take the next integer number. Exact answer is 6.8, but we can't use 6.8, so you have to use 7 number of bolt. When we are using M24 size, that time we require a number of bolt equal to 12, but if we increase the nominal diameter to 30, that is we are using M30 bolt, then the purpose can be solved by using the 7 number of bolt only. A M20 means nominal diameter equal to 20 mm bolt has a shank of 50 mm length. Shank means unthreaded part, and a thread of 25 mm. So length of the threaded portion is given as 25 mm. It is subjected to tensile load of 10 kilonewton. Young modulus of the bolt material is 205,000 Newton per mm square. Strain energy stored in the bolt you have to find out considering both, that is the threaded part as well as unthreaded part. And we have given here the value of dc is equal to 0.8 times of do. In the second part, the strain energy is stored in the bolt if the shank of the bolt is turned down to the root thread diameter. So we have turned the shank and we have made the diameter of the shank is same as equal to the root diameter. Then again you have to find out here strain energy. The strain energy U, that is the total strain energy, is given as 1 by 2 into stress, that is the normal stress square, divided by Young modulus E multiplied by the volume, that equal to area multiplied by length L. So let's consider here we have a bolt. This one is representing the shank, which one is a unthreaded part, and then remaining is a threaded part. Let's say here we have LD is the length of unthreaded part, LT is the length of threaded part. This time we have given the length of the shank equal to 50 mm. So LD is equal to 50 mm, and LT, that is the length of the threaded portion, is given as 25 mm. So to calculate the strain energy here, we require the stress area. For area, we should know the diameter. We have 20 mm bolt. So nominal diameter for the threaded part will be equal to 20 mm. And the core diameter you have to use for threaded portion, that equal to DC, will be equal to, he has given the relation equal to 0.8. So 0.8 times of DO, that equal to 20. So we have core diameter equal to 16 mm. Total strain energy we can compute for the unthreaded part plus threaded part in part 1. Part 2 we'll discuss later on. The given bolt is subjected to external force of 10 kilonewton, which is tensile in nature. So we can very well calculate here stress. Stress you can calculate as force upon area. So we can modify this equation here. We have U is equal to 1 by 2. Sigma we can replace as force upon area whole square multiplied by A multiplied by L divided by E. So one of the A will get cancelled here, and we have strain energy is equal to 1 by 2 into F square. Numerator A is cancelled with denominator, so multiplied by L divided by 1 area is left multiplied by E. So this formula we'll use here because F is common to both and the Young modulus also common. Otherwise we have to calculate sigma for unthreaded part and the threaded part. So that is the lengthy part. This will do the quick solution. So we have total strain energy is consist of the strain energy in the threaded part, that is UD, plus strain energy in the unthreaded part, that equal to UT. So area will change and the length will change, otherwise everything is remain same. So we can take out here 1 by 2 common, even f square is taken common, divided by egg modulus can be taken common, and in the bracket we left here with L. First you have to write down here the length of unthreaded portion divided by area of the unthreaded portion, plus we have length of the threaded portion divided by area of the threaded portion. Area we can write as pi by 4 into d square. So we have 1 by 2. Force you have to take in Newton is 10 kilonewton is 10,000 square of it. Young modulus value we have recorded is 205,000 Newton per mm square. So we'll substitute and solve again. So you have to substitute for young modulus equal to 205,000 multiplied by length of unthreaded portion equal to 50 divided by cross section area, that will be equal to pi. 4 will shift in numerator, multiplied by the nominal diameter equal to 20, and you have to make a square of it, plus the length of the threaded portion equal to 25 divided by pi by 4. 4 will shift in numerator, and we have the core diameter for thread portion is 16. So we have to divide by 16 square. Solve this, you will get the total strain energy. Let's check the unit here. Force we have taken in Newton. So we have Newton square divided by Young modulus is Newton per mm square. So we have Newton mm square. Area we have taken as mm square, and the length L we have taken equal to mm. So mm square cancel, Newton is cancel, 1 Newton is cancel. This answer will come in Newton mm. So total strain energy U will be equal to 69.14 will be Newton mm. In the second part, that is a part B, we have to take the diameter of the unthreaded part and the threaded part is same because the shank is turned here. So diameter will remain same here for both. This time we have to take the value of DO, that is the diameter of the threaded portion will be DD is same as equal to diameter of the core equal to 16 mm. So in this equation area will be common, only length will vary. So total strain energy will be equal to 1 by 2 f square divided by area is common divided by Young modulus into the length of unthreaded portion plus length of threaded portion. Let's check what is this value. We have 1 by 2. Again we have force is equal to 10,000 Newton. So we have 10,000 square divided by area will be equal to pi by 4. So 4 will shift in numerator. Both the unthreaded and the threaded part has a diameter equal to 16 mm. So multiplied by 16 square, again multiplied by denominator by Young modulus, which is equal to 205,000, and in numerator you have to take the sum of unthreaded part plus threaded part, that equal to 50 plus 25. So basically this is a technique used to increase the strain energy by grinding the diameter, or you can make here a hole so that the entire bolt can be made of uniform strength. That topic we'll discuss just now. In this case you will get the strain energy equal to 90.98 is Newton mm. So in the first case we have U1, in the second case we have U2, and we have U2 is greater than value of U1. So it is always better to grind the unthreaded part to the same diameter of the core, or we can make the cross section area of the unthreaded part equal to threaded part, so that our strain energy will increase, and if the strain energy will increase, then the bolt can absorb the maximum impact energy and also resist the rupture. So this method is normally preferred whenever we are using the bolt where we have the impact will take place. Just now we have shown here, if we are using the bolt having unthreaded part has a diameter equal to DO and the threaded part has a diameter equal to DC, in that case we have strain energy equal to U1, and if the entire diameter is made equal to DC, then the strain energy equal to U2. So in the first part we have taken the two different diameter and we have calculated the value of U1 equal to 69.14, and second part we have taken the single diameter equal to DC and we have calculated the value of U2. What we observed is that the value of U2 is greater than U1. So naturally there is a change in strain energy in the unthreaded part and the threaded part. Just now we have introduced here the strain energy U, which one is given as 1 by 2 into sigma square divided by Young modulus multiplied by area multiplied by length. And the second equation we have used is 1 by 2 into force square multiplied by length and divided by area divided by Young modulus E. And this time the bolt is subjected to the tension force equal to F. Same force will be exerted for both portion. So we have strain energy in the case of unthreaded part will be naturally lower than the strain energy in the threaded part because of area. Area is lower, so the strain energy will be higher. This is just proved. So we have strain energy in the case of threaded part. So if the strain energy will be different in both the part, then the impact absorbed by the threaded part will be more and less in the case of unthreaded part. So there is a difference in the strain energy of the unthreaded part and the threaded part. When we say the bolt is of uniform strength, in that case we have to equate the value of unthreaded part with the threaded part. So if both the part, that is the threaded part and unthreaded part, will absorb the maximum amount of energy which one is absorbed by threaded part, then it will be called as uniform strength. So for uniform strength, strain energy for the unthreaded part must equal to the strain energy for the threaded part. The strain energy for the unthreaded part can be written as 1 by 2 F square multiplied by length of unthreaded part divided by Young modulus E divided by area of unthreaded part AD must equal to 1 by 2 F square into length of threaded portion divided by Young modulus divided by area of the threaded portion. I am not use here symbol A0. Basically symbol A0 means pi by 4 into DO square, and AD will have modified value that is given as pi by 4 into new diameter of the unthreaded part, that is DD square. So F square divided by Young modulus is get cancelled on both sides, and if I assume the length of unthreaded part is same as equal to length of the threaded part, in that case we must satisfy the condition that area of the unthreaded part AD must equal to the area at the threaded part. So you have to reduce the area of the unthreaded part equal to the area of the threaded part. Then we can attain the uniform strength, that is both the part will attain the same strain energy. So you can make the area of the unthreaded part equal to threaded part. We have two choice. In the previous example, we have to machine the unthreaded part. That is one solution. Second solution is that we have to make the hole here. So make a hole in the unthreaded part of size equal to dh such that this condition is satisfied. So if we have a hole is made here, in that case we have cross section will be equal to DO will be the outside diameter, DH will be the inside diameter. So area of the unthreaded portion will be equal to pi by 4 into DO square, and this diameter equal to DH. So this time we have AD must equal to pi by 4 into nominal diameter square minus the hole that you have drilled, and you can calculate here what is the size of the hole required for uniform strength of the bolt. And we can equate this value with the core area, that equal to pi by 4 into DC square. So in many applications like connecting rod, mechanical presses and the power hammers, the bolts are subjected to the shock or impact load. In such cases, the bolts are designed to absorb the maximum impact energy and also to resist the rupture. What we have just shown in the previous problem is that in a regular case, the maximum part of energy is absorbed in the threaded portion and less energy is absorbed in the unthreaded portion because the area is larger and we have strain energy is inversely proportional to area. If we assume the length of threaded and unthreaded part is same, length of threaded and the unthreaded portions are same. So in that case, the one solution to increase the strain energy is to reduce the diameter of the bolt. That can be done by turning or drilling. So in turning, we have to machine the surface and drilling you have to make the hole. The stresses developed in the shank increases and thus energy absorption increases. So stresses will increase, the strain energy will increase, and therefore the claim is made that the energy absorption will increase. And another advantage is that due to this the stresses are relieved at the threads. So if you are drilling the shank and they will ask you to calculate the diameter of hole, so use this equation. Pi by 4 will get cancelled and we have simple equation is do square minus ds square equal to core diameter square. What is the diameter of the hole? We are interested in the diameter of the hole that must be drilled in M50 having nominal diameter equal to 50 and the core diameter equal to 44 bolt, such that the bolt become the uniform strength. So whenever we have uniform strength, we have to make diameter of the threaded portion with hole is same as equal to the core diameter. The bolt is given as M50, so we have DO is equal to 50 mm. Directly we have given here the core diameter DC that equal to 44 mm. Required hole diameter you have to find out and the condition is given is uniform strength. So for uniform strength, the cross-sectional area of the unthreaded part with hole must equal to the cross-sectional area of the threaded part. So we have pi by 4, outer diameter is DO square, we have hole diameter equal to DH square must equal to pi by 4 diameter of the core and you have to make a square of it. Pi by 4 and pi by 4 is cancel out. We have DO square is same as equal to 50 square minus we have hole diameter square and we have core diameter is given as 44 square. The hole diameter required for uniform strength will be equal to 23.75 mm. In the second question on the uniform strength, we have to find out the radius. Previously, we have to find out diameter. So be specific about what is requirement. This time require the radius, not the diameter of the hole to be drilled in a shank part of a bolt. To make the bolt of uniform strength, the nominal diameter is 10 mm and the core diameter you have to take as 0.84 of the nominal diameter. So we have given here the nominal diameter D, which is equal to 10 mm. And we have given the relation for core diameter is equal to 0.84 of nominal diameter, that will be equal to 0.84 multiplied by 10 will be equal to 8.4 mm. For uniform strength, we'll just equate the cross-sectional area of the unthreaded part with the hole is equal to cross-sectional area of the threaded part. That is, we have pi by 4 multiplied by DO square minus hole diameter square must equal to pi by 4 into core diameter square. Again pi by 4 and pi by 4 will cancel out. We have DO is equal to 10 square, hole diameter we have to find out, and the core diameter equal to 8.4 square. Diameter of the hole required will be DH is close to 5.42 mm. But remember here, we are not interested in diameter, rather we are interested in radius. So we have RH will be equal to DH divided by 2. 5.42 divided by 2 is 2.71 mm. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.